Welcome to our talk about non-Clairvoyant dynamic mechanism design with budget constraint and beyond. I'm Yuan Deng from Google Research, and this is based on joint work with Vahab, Mirrokni, and Songzhu, both from Google Research. Selling online advertisements via repeated options inspires the research on dynamic mechanism design. In comparison with static mechanism design, one can incorporate many interesting new features in dynamic mechanisms. For example, dynamic reserve pricing or buyer throttle. More importantly, dynamic options open up the possibility of evolving the options across time to boost both the welfare and revenue. In particular, the revenue gap between static and dynamic mechanisms could be arbitrarily large. However, in spite of a large body of research in dynamic mechanisms, most previous research focused on the exposed individual rationality constraints only, while the environments in practice could be much more complicated. For example, the buyers could have budget constraints. In this paper, our main objective is to understand how to design dynamic mechanisms under general constraints. To begin with, let me introduce our Bayesian dynamic environment. In this talk, I will mainly focus on an environment with a single bidder, while all our results can be extended to multiple bidders. In our environment, we consider repeated options. We assume that there is one item arriving at each stage. Upon the arrival of the item, the buyer can observe their private valuation VT for the item at stage T, which is drawn independently from a distribution at T. Here, the distribution is independent across rounds, but not necessarily identical. After that, the buyer can submit their bid to the seller. In this dynamic environment, the seller must sell the item at stage T. And here, the allocation rule and payment rule of the seller can depend on the buyer's historical bids as well as the seller's prior information. We further assume the buyer's utility is quasi-linear and additive across rounds, and moreover, the buyer is a long-term utility maximizer. As the buyer is a long-term utility maximizer, we need to define what do we mean by incentive compatibility, especially dynamic incentive compatibility. So here, one needs to be careful about definition because the buyer's optimal strategy for the current stage can potentially depend on her future strategy. So one natural choice to assume the buyer's future strategy is to say that the buyer would play optimally in the future. So our notion of dynamic IC would be the following. For every stage, reporting truthfully is an optimal strategy for the buyer, assuming she will play optimally in the future. However, this definition is difficult to operate on because it has an optimization problem within it. It turns out that there is an equivalent definition by backward induction. So instead of assuming the buyer plays optimally in the future, we assume the buyer always plays truthfully in the future. So in other words, the buyer reporting truthfully would be a strategy that maximizes the buyer's current utility and the buyer's continuation utility. And here, when we compute the continuation utility, it would be a function that only depends on the buyer's historical bids, because we assume the buyer will play truthfully in the future. With a well-defined notion of dynamic IC, I will introduce a key concept in dynamic mechanism design, which is clairvoyance. So on a high level, a clairvoyant environment would be an offline environment, while a non-clairvoyant environment corresponds to an online environment. In the clairvoyant environment, basically the seller knows the sequence of the valuation distribution in advance. As a result, the allocation and payment rule at a particular stage T to depend on this entire sequence of distribution as well as the buyer's historical bid. And when we talk about clairvoyant dynamic IC at a particular stage, we only need the incentive compatibility to hold for the known future sequence of distributions. On the other hand, a non-clairvoyant environment would be an online environment. In this environment, the seller does not know the time horizon capital T, and also the seller can only learn the distribution FT at the beginning of the stage T. As a result, the allocation and payment rule at stage T can only depend on the distribution knowledge up to stage T, as well as the buyer's historical bids. And moreover, we require a much stringent notion of dynamic IC in the non-clairvoyant environment. Basically, we require the dynamic IC to hold for any possible time horizon T, as well as any possible future sequence of distributions. So in summary, non-clairvoyance requires much less assumption than clairvoyance, which makes it more realistic. On the other hand, we do demand a much more stringent dynamic IC notion in a non-clairvoyant environment. So in this paper, we propose a new mechanism design framework for both clairvoyant and non-clairvoyant dynamic mechanisms with public constraints. Two canonical constraints will be as post IR constraint and budget constraint. For as post IR constraint, we require that the cumulative utility of the buyer should be non-negative. As for the budget constraint, we require that the total payment of the buyer should not exceed her budget. It's worth mentioning that in a non-clairvoyant environment, this constraint must hold at the end of every stage, because every stage could potentially be the last stage. With our design framework, we are able to design a competitive non-clairvoyant mechanism under as post and IR and budget constraint, which achieve non-trivial approximation against revenue optimal clairvoyant mechanism. One caveat of our mechanism is that we do assume a large budget, which means that the buyer's per round valuation should be tiny compared to their budget, which is well motivated in the online advertisement market. We highlight that the approximation ratio of our mechanism is independent of the number of buyers, and also is against an adaptive adversaries. For comparison, previous work show 5 approximation for and the environment without budget constraint. And there is also 2 approximation lower bound for an environment with single buyer and as post constraint, or as post IR constraint only. For the remaining of this talk, I will mainly focus on introducing our mechanism design framework. So when we try to design our mechanism design framework, we have 2 goals in mind. The first goal is simplicity. Basically, we would like to reduce the descriptive complexity of dynamic mechanism. So the most general dynamic mechanism could have exponentially large descriptive complexity because it can potentially depend on the buyer's historical base. And more importantly, we would like to design a non-clairvoyant mechanism that can achieve non-trivial revenue guarantee against the optimal clairvoyant mechanism. So in other words, we would like to establish the connection between clairvoyant mechanisms and non-clairvoyant mechanisms. To do so, let's look at our end goal, the non-clairvoyant mechanism, and try to characterize non-clairvoyant dynamic incentive compatibility. So let's recall what is non-clairvoyant DIC. So non-clairvoyant DIC requires that at any stage T, the dynamic IC should hold for any possible time horizon T and any possible future sequence of distributions. So it's quite straightforward to see that non-clairvoyant DIC implies stage IC, which means that the mechanism in each stage should be choosable in isolation. And the proof of this is very straightforward because every stage could be the last stage. It turns out that non-clairvoyant DIC also implies a stronger property, which we call history utility independence, which means that the expected utility per stage under choosable bidding should be history independence. In other words, the buyer's historical base should have no impact on the buyer's future expected utilities. To have a better understanding about history UI, let me give you a quick proof when there is only 2 stages. First of all, history UI naturally holds for the first stage, and we will show that history UI stands for the second stage. So first of all, we have stage IC for the first stage, which means that the payment rule in the first stage, denoted by P1, should truthfully implement the allocation rule in first stage, which is denoted by S1. So furthermore, we have dynamic IC. So the difference between stage IC and dynamic IC is that in dynamic IC, we have an additional continuation utility. And in the definition of our dynamic IC, we already assume that the buyer will do truthful bidding in the future. As a result, the continuation utility will only depends on the buyer's fee in the first round. Therefore, we are able to combine the payment and the continuation utility and get a function P'1, which basically captures the difference between the payment in the first round as well as the buyer's continuation utility in the second round. Now, since this should be incentive compatible, we also know that P'1 should also truthfully implement the allocation rule as well. By the famous Mason's lemma, we know that given a fixed allocation rule S1, the payment rule that can truthfully implement X1 should be unique up to a constant. As a result, the difference between P1 and P'1 should always be a constant, which concludes the proof. We would like to highlight that although history UI requires that the expected utility should be independent of the buyer's past bid, the expected utility could still depend on the prior information on the SNT level, and we will leverage this fact extensively in the design of our competitive mechanisms. And moreover, it's not hard to see that stage IC plus history UI is an if and only if characterization of non-clairvoyant DIC. So for a mechanism that's HUI, basically it means that the bias historical bit has no impact about the future. As a result, once the mechanism is stage IC, the mechanism will be dynamic IC. So now we have a very nice and clean characterization of non-clairvoyant dynamic mechanisms. So a natural question we'd like to ask is it possible to convert any clairvoyant dynamic IC mechanisms to a stage IC plus HUI mechanisms? And the answer is almost yes. And in our reduction, we are also able to reduce the descriptive complexity of the mechanism. So first of all, we start from any clairvoyant mechanisms. And in its general form, its allocation rule and payment rule can depend on the historical base of the bias. In the first step, we will apply a procedure we call symmetrization, which works for any constraints. After symmetrization, we obtain our lossless history compression mechanisms. In this mechanism, instead of checking the bias historical base, we only need to check two types of information. One is the sufficient information for us to recover the bias constraints. And here, it turns out that for some constraint, the information can be represented by one number. As we mentioned before, for S post IR, we only need cumulative utility. For budget, we only need total payment. One caveat here is that we do need to check one additional thing, which is the bias expected future utility, which is a forward-looking information. And in this way, it's not very desirable. In the second step, which we call payment realignment, this is not always feasible, but is feasible for many practical constraints. By payment realignment, we are able to get rid of the expected future utility and obtain a mechanism that is both stage IC and HUI. And we would like to highlight that payment realignment is indeed a if and only if condition for a clairvoyant mechanism that is able to be converted to a stage IC plus HUI mechanism. To have a better understanding of payment realignment, I will give you an demonstrating example. Actually, this example also demonstrates the infinite gap in terms of revenue between static and dynamic mechanisms. So in this example, we have two stages, and each stage has a discretized version of the equal revenue distributions. Means that the bias probability is 2 to the I with probability 1 over 2 to the I. And the difference between stage 1 and stage 2 is that in stage 1, the index of I is between 1 to the n, while in the stage 2, the index is between 1 to 2 to the n. So since we have an equal revenue distribution for both stages, then a static mechanism or selling separately using the optimal static mechanism gives revenue at most 2 per stage. Next, I will show you a dynamic mechanism that can achieve much more revenue than 2 per stage. In the first stage, we will run a first price auction. So basically, after receiving the bias bid B1, we will allocate the item and charge the bias bid. As a result, if the bias true valuation is B1, then her utility in the first stage will be B1 minus B1. In the second stage, the allocation will be independent of the bias bid on stage 2. And what we are doing is that we will give the item for free with probability B1 divided by 2 to the n. And here, the probability will depend on the bias based in the first stage. A simple calculation can show that the bias expected utility in the second stage will be 1. As a result, in this mechanism, we achieve revenue n because we do a first price auction in the first round. And also, this mechanism is dynamic IC, especially for the first stage, because the summation of the bias utility in the first round plus its continuation utility in the second round will be V1 minus B1 plus B1, which is exactly V1. And this is independent of the bias bid in the first round. However, it's not hard to see that the dynamic IC property highly depends on stage 2. So if we have a wrong prior information about stage 2, then the dynamic IC property is likely to collapse. And even worse, it's entirely possible that stage 2 does not even exist. So next, I will try to apply payment realignment to resolve the issue. So what we will do is that in the first stage, instead of offering a first price option, we will offer a give for free mechanism. As a result, we are not going to charge anything in the first round. In the second round, we will first charge a payment B1 and then run the same mechanism as before. So in this way, the bias expected utility in the second round becomes 0. So basically, what we are doing here is that we defer the payment from the first round to the second round. while keeping the allocation the same. And after payment realignment, we can see that the bias expected utility in the second round is always 0, which is independent of the bias bid in the first round. And moreover, in the first round, we are running a give for free mechanism, which is stage IC on itself. As a result, the dynamic IC property will be independent of the stage 2 entirely. So when the payment realignment is possible, we are able to convert any clairvoyant mechanism to a stage IC plus HUI mechanism. It turns out that for many practical constraints, payment realignment is possible. For example, as post IR budget constraint and ROI constraints, etc. So in summary, our reduction shows that it's without loss of generality to consider lossless history compression mechanisms, which we call LHC mechanisms. In this mechanism, basically we compress the history into a state, and the state will carry the sufficient historical information for us to recover the bias constraints. And furthermore, we also require the mechanism to be stage IC plus HUI. So with our mechanism design framework, we are able to design our competitive mechanism. In this short talk, I will not go deeply into our design of the mechanism. And here I will highlight one challenge. So here we would like to do revenue optimization. So intuitively, we cannot avoid running Marsden's option, because Marsden's option is in the optimal when there is only one stage. However, when there is budget constraint, it will be suboptimal to always run Marsden's options for all the buyers. Because intuitively, if the buyer's budget has been exhausted, then we should exclude this buyer. However, there is some conflict between how to exclude the buyer and how to ensure HUI. Remember that HUI is a property that saying that the buyer's future utility should be independent of their past bids. So the key idea we use here is that we will exclude the buyer whose budget has been exhausted so far on the ex-ante level. So in this way, the buyer's future utility will still be dependent on the prior distributions, but it would totally be independent of the buyer's historical bids. As a summary, in this paper, we propose a framework to design clairvoyant and non-clairvoyant dynamic mechanisms in general environments. And furthermore, we use our framework to design a non-clairvoyant mechanism, achieving a constant approximation against revenue optimal clairvoyant mechanisms under ex-post IR and budget constraints. As for future directions, it will be very interesting to design non-clairvoyant mechanisms for other constraints, for example, ROI constraints. And moreover, it would be an intriguing open question to consider dynamic mechanism design beyond quasi-linear or additive bias. Thank you for your attention.